Welcome. Today we're diving into the world of analysis of variance, or ANOVA, fundamental concept in statistics and experimental design. ANOVA is used to test the equality of means across more than two groups, especially when the data comes from normal distributions. Imagine you're comparing the effectiveness of different medicines or treatments. ANOVA helps you determine if the observed differences in outcomes are statistically significant or just due to random variation. The experimental setup, conditions, and objectives all influence the type of design and model you should use. In this video, we'll break down the basics of experimental design, introduce key models, and walk through a practical example to make these ideas clear and approachable. Let's explore the models used in experimental design, focusing on one-way and two-way classifications. In a one-way classification, we analyze the effect of a single factor with multiple levels, like different dosages of a medicine. Each level represents a group, and we observe responses such as the time taken for a medicine to reduce fever. The general linear model for this setup includes a mean effect, specific effects for each group, and a random error term. These models often use a design matrix filled with zeros and ones, indicating group membership. However, not all parameters in these models are uniquely estimable unless certain restrictions are applied. This leads us to the concept of reparameterization, ensuring that our estimates are meaningful and unique. Make things concrete, let's consider a medicine experiment. Suppose we have three dosages, 2 mg, 5 mg, and 10 mg given to patients with fever. Each dosage group has a different number of patients, and we record the time it takes for the medicine to bring down their temperature. The model expresses each observation as the sum of the general mean, the effect of the specific dosage, and a random error. In practice, we often need to impose restrictions, such as the sum of the group effects being 0, to ensure unique parameter estimates. This reparameterized model allows us to use least squares or maximum likelihood estimation to analyze the data effectively. By understanding these steps, you'll be better equipped to design experiments and interpret ANOVA results with confidence. Now let's clarify two important concepts, estimability and reparameterization. In linear models, not all parameter combinations can be uniquely estimated if the design matrix isn't a full rank. Estimability refers to whether a particular linear function of parameters can be determined from the data. Often, only contrasts, differences between group effects, are estimable. To resolve this, we reparameterize the model by imposing restrictions, such as setting the sum of group effects to 0. This ensures that the least squares or maximum likelihood estimates are unique and interpretable. Understanding these concepts is crucial for correctly analyzing experimental data and drawing valid conclusions from ANOVA.